This is going to be an application of equilibrium in a way that kind of looks at some of those same ideas from before. How do things change? How do things shift? But to introduce this, we're going to actually talk about how we kind of stress this equilibrium. And then a result of that, where does it shift? Firstly, let's go ahead and take a look at this expression. You have A plus B. That yields, or this equilibrium with C and D. You have a K of 2. And in this case, you kind of just generically have some equilibrium amounts. Again, this is very much a made-up equation. Nothing really actually works this way. But A has 1 molar concentration, B is 2, C is 2, D is 2. And again, if you plug that into K, or at least you plug that into the expression, you'd end up getting 2 as a result, which again shows you that it's at equilibrium. Now, let's mess with the equilibrium a little bit. Right? Let's stress the equilibrium some. To stress it, we can do a couple of things. One, let's go ahead and add some extra A. All right, so let's say, again, we arbitrarily add some amount of A, and then we're no longer at equilibrium. Why are we no longer at equilibrium? Well, remember, in order for something to be at equilibrium, or a sample of substances to be at equilibrium, the ratio of products over reactants has to equal, in this case, 2, has to equal to K. So the moment you add some extra A, you actually kind of mess with that ratio. You no longer have these numbers work out to where they divide each other and get 2. Now, again, we're talking about just at that moment, right? So if I have a mixture, if I mess with it just at that specific moment, it's not going to be at K anymore. So you're no longer at equilibrium. Same thing with the second one right here. If I collect and remove B, right? So if I take B and get it out of the mixture, what happens? Well, once again, equilibrium has been disturbed. That ratio of products over reactants has been changed. So no longer does that ratio equal to 2. No longer at equilibrium. Therefore, this equilibrium has been stressed. Finally, we can heat up the equilibrium mixture. How does that affect our equilibrium? Remember, the fundamental definition of equilibrium says that the forward and reverse reactions are occurring at the same rate. So if we mess with the temperature, that means we're changing the rates. We're changing how this reaction is going to proceed because we mess with, again, the speed at which it goes forward and the speed at which it goes backwards. So again, we're stressing it, right? We're talking about no longer having a K that's equal to just 2. So with LeChatelier's principle, what that's saying is that we can actually predict how the stress can be relieved when an equilibrium experiences that stress. Right, that's kind of a fancy way of how all this works. And once again, LeChatelier's principle is basically saying that if you were to pose a stress, or if you were to cause a change to an equilibrium or to an equilibrium mixture, you can have a predictable shift so that that stress is relieved. This principle can be used to predict a new equilibrium position. So if you remember, the equilibrium position is that combination of concentrations or pressures, depending on the equilibrium. But it's, again, the specific numbers that will give you a ratio of K. Right? That will give you the exact amount of K, whatever that number is. In the previous example, that was 2, but of course, different equilibrium have different Ks. But overall, right, is any set of concentrations or pressures at equilibrium specifically. Let's see how this can be put into action. So let's go ahead and take a look at this equilibrium mixture. You have N2, H2 that form NH3. Right now we're assuming that at equilibrium. We're assuming that this specific mixture of 0.399, 1.197, 0.202 molar, that mixture right there is going to be at equilibrium. Right? That's a position. So again, if I were to take these products and divide it by the reactants according to the ratios and so on and so forth, you would get 5.96 times 10 to the minus second power. So this is one equilibrium position. If you were to just inject a bunch of N2, right? So enough N2 so that it equates to 1 molar and N2 just added in there, what happens? Well, at that moment, the concentration of N2 shoots up to now 1.399, right? Because it started off at 0.399 as at equilibrium. You throw in an extra 1 molar, yeah, it's going to go up to 1.399. Now, at that moment, Q will be less than K. Now, why am I introducing Q again? Well, remember, anytime you're not at equilibrium, right? Anytime you know you're not at an equilibrium position, you can use Q to figure out where you are, right? So if Q now, when I use that new value of 1.399 to plug into that expression of products over reactants, the Q will end up being less than K. Right, Q will be less than K. And as a result, we know that when Q is less than K, the reaction, the equilibrium will shift towards the right now to reestablish a new equilibrium. And so kind of equate this. If you're going to reestablish a new equilibrium or reestablish a new equilibrium position, you're basically relieving that stress. Right? The stress was adding the extra N2. Let's relieve that stress. Let's shift to a certain direction, in this case, shift to the right. So after some time, equilibrium is reestablished, and now you get a new equilibrium position, which is the collection of these 3 values. So if you're familiar with this idea of Q, right, the idea that you have some mixture and you want to compare it to K, if you have this Q, that Q will always inform you how the reaction will relieve stress. And all we're doing now is saying, okay, we had an equilibrium, we messed with the equilibrium, and now let's figure out what direction it's going to go to. If you were to go through again and go ahead and recalculate K using these values or plug it into the expression, you would once again get 5.96 times 10 to the minus second power, which is the same K from up here. So how did this equilibrium relieve stress when you injected a bunch of N2? It would shift to the right. There's almost some amount of maybe intuition you have here, right? If you overload one side of the equation, in this case, if you overload the reactant side, it's then going to shift to the right to sort of relieve it. You're going to consume a bunch of reactants and then generate a lot more products. Let's see what that looks like as a chart. So if I have some H2, NH3, N2, right? We're saying this section right here. This is going to be that time, all this time right here, where your partial pressures, or again, concentration, doesn't really matter. Those amounts are going to stay constant. Why? Because we're at equilibrium. These amounts don't change, or the ratio, the concentrations and the pressures don't change. But at this moment, right, remember we added a bunch of stuff, right? I might have incorrectly said, or in my example earlier, I might have said N2, but in this case, let's add H2. Either way, it doesn't really matter. You increase the amount of H2 at this moment. So what happens here, again, is that partial pressure, aka the concentration or the amounts, at that moment, right, it's going to increase significantly here. The other ones, right, at that moment might be whatever it is to start. But then what's going to happen? It's got to shift to the right. Because once you add this, you're going to end up using up a lot of N2 at the same time. So this decreases, right? You use up some N2, some of the reactant side stuff. And your NH3 stuff goes up, right, because you produce that amount. And then this H2, right, even though you have this big spike at first, will start to also decrease because it gets used up as well as you continue shifting towards the right. Eventually, you're going to, once again, reestablish equilibrium here because the concentrations will eventually even out. And therefore, the rates, right, the rates at which you go to the forward direction and the reverse direction will eventually re-equal each other. And so you've reestablished a new equilibrium. What happens to the amounts? Well, H2 goes up, right? So the amount of H2 has increased some. The amount of NH3 has also increased some. The amount of N2 has decreased as a result. But of course, this is not something that just happens on its own. You have to cause a stress to happen. You force it to shift because you stress it. Let's go and walk through this example. So this, again, same equation, same equilibrium. You have a K, and you have 5.96 times 10 to the minus 2, which is just, again, that K that you can use to sort of remember which side will be, or the amount, anyway, of products versus reactants, that ratio. Let's go and see what that stress is. The stress is added to an equilibrium mixture by injecting hydrogen gas, right, this stuff right here. A new equilibrium position is allowed to be established. How does the value of K change? The value of K change? None, right? Changing the concentrations of substances does not change K, right? The ratio will eventually always be that same value of 5.96. The actual numbers of products, the actual amounts of reactants, those can change, right? That's because you have different equilibrium positions, but ultimately K will always be the same. Which side of the equilibrium was stressed? So if I added hydrogen gas, right, I stressed the left side effectively. I'm adding a bunch of junk to the left side, so I'm making the equilibrium be messed up because I added extra stuff to the left. And so 3, what direction does equilibrium shift? It's going to shift to the right. Now, relative to the first equilibrium position, how does the concentration of each substance compare in the new equilibrium position? So this right here is going to be a little chart that's going to help me keep track of it, right? So I have N2 at equilibrium, H2 at equilibrium, and NH3 at equilibrium, all pre-stress, right, before I added any extra H2. And then post-stress, right, once it reestablishes equilibrium again, how do those amounts compare? All right, so N2, right, so let's go and talk through this. First of all, my N2, right, I didn't change the amount of N2 when I stressed it by introducing hydrogen gas, right, so I didn't change this amount yet, but to reestablish equilibrium, it's going to shift to the right. You're going to use a lot more reactants, so the N2 at equilibrium before the stress will be less than the post-stress amount. What about H2? Well, H2, right, we're going to increase the amount significantly by injecting a lot of it, so that's going to spike up, but then eventually it'll reestablish equilibrium. Well, when it reestablishes equilibrium, it's going to overall have a greater amount after the stress has been relieved. So this is actually going to be greater as well. And then finally, NH3, right? How will that compare at equilibrium versus that NH3 post-stress? Well, again, pre-stress, you end up making a lot of NH3 here, right? So you end up, pre-stress, you have some amount here, but then as it shifts right, it's going to use a lot of it. So that's going to be, again, greater after equilibrium as a result because you made some stuff. All right, actually, I'm sorry, I think I made one mistake here. Let's go back here. This is going to be this way instead, right? So your equilibrium post-stress is going to have less amount of N2 at the end. All right, and to finish this up, you have one practice problem. Let's go ahead and see how we can mess with this. For each of the following changes, let's see how that direction, what direction it will go. The first one, we add O2 to the mixture, so we increase the amount of O2 here, and that's our stress. To relieve it, it will shift to the left, so the proper response here is shift left. All right, now, if you're not entirely sure, remember, how does this compare K and Q? Well, if my Q, right, now that I've added some stuff here, I'm going to have greater amounts of products. All right, this is going to be bigger. Right, this is going to get larger. My reactance stays the same, so that means my Q is greater than the K that I had originally. And when Q is greater than K, it's going to shift to the left. SO2 is collected from the mixture, so I've taken this stuff out, right? Take it out. So how do I stress it? Well, it's kind of like I dug out some of the right side, so it's going to shift to the right to reestablish equilibrium. So that's going to be shift right. Let me get rid of these now. By the way, these are all independent, right? So the first one is the shift that, or is the stress that occurs to, one mixture, and then two, that's going to be a completely separate mixture, starting at the same point, and then we're going to take away some SO2. Here's a third mixture, an entirely different mixture. If I took SO3 and added it to the mixture, I'm going to stress it by increasing the amount on the left side. And so to relieve that stress, it's going to shift to the right. Right? So you can make the argument dealing with Q and figure out how it compares to K and stuff, but this again will shift right. And finally, argon gas is added to the mixture. Well, if you notice, argon isn't even in this substance at all, or in this equilibrium mixture at all. And so even though you have extra particles in the container, right, it is argon after all, it is a gas. You actually don't end up affecting this equilibrium because this equilibrium is only affected by these specific substances. So in this case, there'll actually be no change. All right, that'll do it.